Okay, we are going to begin chapter 6. All right, so far we have discussed atomic theory. So we had Democritus had the idea of the atom. Excuse me, I got a little chuck there. And then Dalton had his own atomic theory, proved that the atom existed, so they were indivisible. That we can rearrange them, we can't create them into new things. Well, then Thomson was messing with his cathode ray tubes, and he was able to discover the presence of the electron. And then he knew if we have negatives, then we got to have positives. And so Rutherford performed his Goldfull experiment. He figured out we have a nucleus, and that's where all the positive charges are. And then Bohr developed a model to help us understand the way it behaves. And then the most current model is that of the quantum mechanical model. The QMM, the electron cloud model, has a couple of different names. And so we're current, like you've traced it all the way from where it was to where it is now. The most current model of the atom is the quantum mechanical model. Well, now we want to talk about the other tool that we use a lot in chemistry, almost daily, and that's the periodic table. So this is going to go with chapter 6, section 1. You don't have to write down objectives, but let's just talk about some of the things that we're going to do. I want you to be able to explain how the elements are organized on our table. I want you to compare an early table to a modern table. We're going to explain something called the periodic law. And then, of course, we're going to be able to describe the 3 classes of elements based on location and their properties. And then any element that I give you, you should be able to then put in one of those classifications as metal, non-metal, or metalloid. So it looks like a lot to get done, but most of these are pretty simple tasks, and we're going to go through them slide by slide. So let's start with our very first person to organize any functional table, and it was a man named Dmitri Mendeleev. He created the very first working periodic table. He took all the elements that we knew about and he grouped them by their similar properties. So how did they behave? And then within those, when he got those in a group, he ranked them by their atomic mass. And when he did this, he started to notice that patterns were developing. And he's like, okay, well, obviously something is missing here. The patterns were so distinct and so easily read. He actually predicted the chemical properties of things that had yet to be discovered. And we found out he was right after we discovered things like germanium. He was actually able to tell us the properties of it before we ever actually found it in nature. Mendeleev's is a pretty great story. He lived in Siberia, which is a very desolate place in Russia. And he didn't have a lot. His family was pretty poor. His mother and him actually walked almost 1,500 miles to get him into a university because she believed he was so gifted. And the first one they went to did not actually take him. And then they had to go to a separate university. And then they finally took him. And his mother actually ended up dying from the stress of this trip. So, but Mendeleev, he was very successful in his stuff. And he was trying to write his own textbook. He was teaching a class. And through trying to write his own textbook for his students, he was actually able to create the periodic table that we know about today, that we're still using. It's not in the same way, but he gave us the bones and the structure to begin with. This is what Mendeleev's table looked like. And that is nothing like what we have on the wall over there. But what it is basically is he just took these things and he grouped them. And then he ranked them by their atomic masses. And then he noticed that there were just empty spots. And so yes, ma'am. Yes. He noticed those empty spots though, and he was able to say, okay, I bet it has a mass of about 68. And I bet it behaves like this. We good? All right. Well, Mendeleev's table was groundbreaking because we were able to see these patterns and we were able to organize our elements in a meaningful way. Yes.
Back here, it looks like you. I think most would go out like after.
Okay. Yeah, I guess that was maybe some of the style of the time. He actually fought in World War II, and died in World War II. Henry Mosley did. Yeah. So I guess I can see that. But Mosley was able to contribute pretty, and he was young and he was brilliant and a genius. And a lot of people think, have commented that his death and, fighting in war was absolutely a waste and he shouldn't have gone because he was such a brilliant scientific mind and all that stuff. But what Mosley did is he set about to collect all of the data that he could about every element we know. And one of the main things that he collected, if we didn't know it, he found it, and that was the atomic number of every element that was known to man. So, how many protons were present in each of these elements? What is the atomic number? And then he rearranged the table that we had been working with. We've been using Mendeleev's, and we got to Mosley, and he rearranged it by increasing atomic number. And when he did this, he was able to establish something called periodic law. Uh-oh. Okay. The periodic law just is defined as when we arrange our elements by increasing atomic number, there is a periodic repetition of their chemical and physical properties. That's why we call it the periodic table. It has properties that we can predict as they move around the table. Like I can determine where the metals are and where the non-metals are, and if it's going to be highly reactive or not reactive. All of these things can be predicted based on where they're located. So our periodic table is more than just a chart to hold our elements. It's also actually a tool that we can use because of periodic law. If I have an element on the right side of the periodic table, I can assume it's probably a gas because that's where my non-metals are located. And I'd probably have about a 95% chance of being right. But the periodic table is not just a list of the elements, it's a usable tool. It allows us to predict the properties of our elements based on where they are located on this table. Okay. Am I good to move forward? I don't want to. So the modern periodic table, what we already have a copy of, what we are looking at on our wall in the room here, is going to be ordered by increasing atomic number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it just goes on in sequential order like that, and that's how we put it together. We organize each of these into periods. There are 7 horizontal rows that we refer to as periods. And we can predict properties as we read those from left to right. The modern periodic table also has groups. It has 18 individual groups. And things that are in these individual groups, they're in the same column, and they share similar properties. Like everything in group 1 is a highly reactive metal. And everything that's in group 18 is a very unreactive gas. They have very similar physical and chemical properties. And that's why you put things in groups together, because they're similar. So our periods are the horizontal rows. There are 7 of them. And then our groups are the vertical columns. All right. This is just a graphic. You don't have to see. You can see that 1, 2, 3, 4, 5, 6, 7 rows, and then you can count across the top. And there are 18 of those. All right, you don't have to write this down, but just think, who organized the elements first? Who's the first person? Has the funny name. Mendeleev. And what did he do? How did he organize them? What method did he use? Properties and then perfect mass. Perfect. All right, then who did it by atomic number? Moseley. Very good. All right, now ask this question based on what we know. If you needed to replace an element in a reaction, would you want to pick one from the same period or the same group? Group. And why is that? They're going to act the same. Very good. All right. The last 2 objectives were about the 3 types or the 3 classes of elements, which are metals, nonmetals, and metalloids. So our periodic table is done by increasing atomic number. It's arranged into 7 periods and 18 groups. We also can classify our metals, nonmetals, and metalloids based on where they are located on the table. All right. So let's discuss metals because you need to know where they're located on the table and the characteristics of metals. One thing to note is that metals are most elements. About 80% of every element on the periodic table, about 85 actually, percent are going to be metals. So if I had to guess, if I had no idea, if I was given something I've never seen before in my life, and I had to guess if it was a metal, a non-metal, or a metalloid, about 85% chance that it's a metal. because almost all the elements listed on the table are metals. Metals are good conductors of heat and electricity. Most metals, not every metal, but most metals are considered good conductors of heat and electricity. And if we think about some metals that we probably could recognize right off the bat, like copper or aluminum, those are metals that we know about. Yes, Patrick?
Iron.
Iron's one. Those are all great conductors of heat and electricity. Some metals, and we're not every single one, but most of the metals actually have the ability to be malleable, which means we could be hammered into sheets, or ductile, which means to be drawn into wire. Yes. That's exactly right. Copper. And if you think about copper, that's a really good example to keep in your mind when you're thinking about metals because it has these qualities. Malleable. I always think of like if you have a mallet. A mallet is something like a hammer. That's what a mallet is. And I would use that to flatten something out. So hammer it into sheets. Malleable. I'd use my mallet. Ductile. I think about ducts. Ducts are usually, circular, kind of like wire is. So most of the elements on the periodic table are metals. That means they're probably good conductors of heat and electricity, and some of them will be malleable and ductile. You're going to see these in groups 1 through 12, plus a handful of elements that are part of groups 13, 14, and 15. So way more than half. If you start on the left side of the table and move over, you're still seeing metals even over into group 15, and there's only 18 groups. So there's a lot of metals. And those two rows at the bottom, the lanthanides and actinides, those are metals. So about 85% of every element, metal. Okay. This is just a diagram here for us. I just wanted you to, all the metals are in red. You can see here that hydrogen isn't one, but all of group 1, 2, and then all the grade 3 through 12. And then there's a handful of elements over here in 13, 14, and 15, plus all these ones at the bottom. So most of the elements on the periodic table are metals. Well, that leads us then to the ones that aren't metals. They're nonmetals. The second largest group would be the nonmetals. Nonmetals, most nonmetals are gases, but there are liquid and solid nonmetals. Liquid bromine exists as a liquid in its natural state, and it's a nonmetal. Carbon is a solid, and it's probably the most famous of the nonmetals. But most of them are gases. If you look at our periodic table over on the wall over there, the metals have black symbols and the solids have black symbols. The non-metal gases have red symbols. See how like nitrogen, oxygen, fluorine, chlorine, those are the non-metal that are gases. And then there's the liquids are actually in blue. And there's only two elements that exist in liquid at room temperature, and that's bromine and mercury. So there's a reason they have those different colors. Non-net metals are not good conductors of heat and electricity, which I'm very thankful for. Think about the air in this room. It is, all full of non-metal gases. If it conducted electricity, we'd have to be protecting ourselves from the light socket there. Not something we want to do. Yeah. I'm telling you, it'd be a shocking experience. These are going to be found on the right hand or the right upper corner of your table. Again, there's nothing to write down on this slide, but these are our nonmetals over here in blue. So carbon is a nonmetal. I don't know why that keeps blinking. And then here's the rest of our nonmetals. So metals in red, nonmetals over here in blue, which leaves us with this zigzag line and our lime green ones, which are called our metalloids. Yes. What, dear? Yes, you're right. Metalloids are the ones in green. Metalloids have properties of both metals and nonmetals. But how it's going to behave really acts on the conditions. So if you alter the conditions, it may behave more like a metal, or it could be more like a nonmetal. And those conditions we're talking about are things like temperature and pressure. So if we can change the conditions, we can change its behavior. But they generally have characteristics of both. The most famous example of a metalloid is silicon, and I am not saying that incorrectly. Silicone is spelled Silicone. And silicone is a derivative. It's made with a silicon base to it, but it is not the same thing. Silicon is used in computer chips. If you think about all the things in your life, the Chromebook that you're using, the cell phone that you're on, the earbuds, pretty much every piece of technology that you are used to having access to is made possible because of silicon. As a matter of fact, it's so popular in California, where huge places like Google and Microsoft and Apple and all of those places were created. They actually call it Silicon Valley because so much silicon is transported into that region in order for them to create computer chips and technologies with them. So silicon is number 14 on the periodic table. If you're ever confused about where to do your zigzag line, make sure you, kind of go on the outside between carbon and silicon, and it'll help you make that little stair step down. All right. Did you have a question, Patrick? It can be used as mold. You're right. This silicon that I'm talking about, silicone is like a derivative that you can use in like a silicone mold and things like that. It's used in like, I don't know, it has a lot of uses for silicone, but silicon is going to be probably our most famous one. It's not the only one though. These will border our zigzag line on the periodic table. If you start a zigzag between boron and carbon, and you draw a little zigzag line and you just make a little stair step, the things that touch that line are going to be considered are metalloids, except for aluminum. Although aluminum does touch the line, it is not considered a metalloid. It always behaves as a metal. It is not a metalloid. So that is an exception. Metalloids are often called semiconductors as well. Yes. Yes. Our metalloids then are here in green. So like I said, if you want to draw your line here, start between boron and aluminum, and then you just drop it down, make a little stair step. The boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. These are going to be our semiconductors or our metalloids. Yes. These are, they actually behave, this one acts like a non-metal noble gas, and then this one is it acts more like a metal. They're not colored in because they had, at this point when I found this graphic, they had not been named and classified. They're only created in labs, like they don't exist naturally. All right. There's nothing else to write down, but look at the periodic table and see if you can do the skills that are asked of you. Use your periodic table, and I want you to tell me if this is a metal, a metalloid, or a non-metal. All right, find barium. It is number 56. All right, metal, non-metal, or metalloid? Metal. All right, sodium is number 11. What is it? Metal. Copper. I don't even have to tell you a number. What do you think copper is? That's a metal. Good. All right, vanadium is number 23. Metal. Silicon, should know it. It's a metalloid. We just talked about it. It's number 14. It touches the zigzag line. What about arsenic, number 33? What is it? It is a metalloid. It touches the zigzag line. Good job. And if you want to draw the zigzag line on your table, we're going to color our table at the end of the week. You are more than welcome to do that so that you have access to it for your tests and quizzes. Let's see. Last but not least, iodine is number 53. What do you think? It's a non-metal. You're right. Good job. All right, just read the descriptions and to tell me if it's a metal, a non-metal, or a metalloid. A gas that doesn't conduct electricity is a non-metal. Great. Used to make wire. Metal. These will only conduct heat under certain temperatures. Metalloid. These elements are found on the upper right-hand side of the periodic table. Non-metal. All right, I think you've got it. That is chapter 6, section 1.